So it's the matrix part of it.
Matrix point of view.
Instead of looking at the exchange patterns, remember all these monomials, we will encode all the data in matrices. So it's a different way to look at these objects. Maybe I will remember you something, or you remember everything.
I told you I remember nothing.
Maybe I just write the axioms of the exchange pattern. Do you remember we had this graph?
It was a month ago, right?
Yes, maybe more. I don't know. We have this graph with the edges labeled with integers from 1 to n. And we have this family of monomials m, I, t, for all t in the graph, all I.
Sono stata io a dire che potevo cominciare.
Sapevo che era tutto molto
No, non ho mai detto.
Dopo che ci ha accusato di tresca.
Sì, ho fatto una scenata, Lo sai che sono.
So these MIT were monomials. In the ring of polynomials in the variables x1, xn with coefficients in Zp, where P was a commutative group with notation, but not actually.
Come sei fashion oggi?
No, ma io lo so, ormai è chiaro.
L'ho messa da te.
Questo è chiaro proprio. Cioè, lo dicevo anche a lui la cosa.
È la telecamera che sta riprendendo.
Non fare le domande.
Ah sì, sì, è vero.
Cioè io ce l'ho chiaro, bene, va là. Però bisogna mettere le cose quando non ci sono. Ma infatti è la scenata di gelosia, te l'ho detto.
Okay, so we have 4 axioms. This is a monomial. MIT is PI T x1 to a1 xn to a. So these objects have this form. And let me remind you the axioms. Axiom 1, which involves one vertex, say that xi does not divide MIT for all I or t. Axiom 2 involves two vertices. So t prime I. Say that the two monomials attached to these vertices with label I are relatively prime. So if xj divides MIT, then xj does not divide MIT prime. In axiom 3, we have three vertices. T prime, T double prime, labels I and J. And the fact was that xj appears in the monomial MIT, so xj divides MIT if and only if xi appears in the monomial mj prime. Then we had the axiom 4. Maybe I write it here in the first blackboard. Axiom 4. We have 4 vertices: T1, T2, T3, T4, with labels I, j, I. And here we want the quotient mi t2 or mi t1. This is equal to mi t3 divided by mi t4. The substitution. The substitution is that we write m0 over xj instead of xj, where m0 is the sum of these two monomials. So mj t2 plus mj t3. Computed that xi equals 0. Hope everything is correct. Yes. So we also observed that if we know all the monomials attached to the edges emanating from one given vertex, then we know all the exponents that appear in all monomials on the graph. So we start from this observation page, and we write one of these quotient, maybe jt.
So can you repeat the observation? So this is something we proved, or is really intrinsic from
No,
the
this
definition? Observation from the definition.
Immediate observation from this axiom.
So the observation is if we know what the...
If we know all the 2n monomials attached to the edges emanating from one given vertex, then we essentially know all the monomials but the coefficient. I mean, we know all the exponents in all monomials, but we don't know this coefficient.
Sorry, I don't understand. No, you have to repeat. I don't understand. You say if we know all the monomials,
the 2n monomials, then we know all the other monomials.
All the other from all the rest?
Yes, except the coefficients.
Okay.
We know just the exponents.
And this comes
and this will be clear from the new point of view that I'm going to show you.
But you say that this observation comes from the definition?
This comes from the definition, yes. This comes from axiom 4 and maybe axiom 2 also.
You already made this observation
yes.
in the past, okay.
So let's take these two vertices t, t prime with label j. So we fix t and we're going to look at the edge emanating from t labeled with j and call t prime the other vertex on this edge. If we look at this quotient, this is bjt divided by bj t prime, and then we have a product, all I, x, I, b, call these exponents bijt. So we start from t, we look at the edge labeled with j, and we look at this quotient, and these are this form. So we call these exponents bijt. Okay. Of course, since the two monomials mjt and mjt prime are relatively prime, we can reconstruct mjt. Of course, we just know the quotient of these two, so this will be bjt times the product on all I such that bijt is positive of xi bijt. Okay? These are two monomials. These bijt are integers.
Not positive, they are integers.
They are integers, yes, because we are doing the quotient of two monomials. But since these two are relatively prime, what we have at the end, we look at the positive exponents. This comes from MJT. The negative exponents come from MJT prime. So
but you cannot really reconstruct because you don't know.
You cannot reconstruct the
you
coefficient.
cannot reconstruct that. Okay, so that is exactly.
Yeah, actually today we could also think of all these coefficients to be 1, if you prefer. But in any case, MJT prime, this is PJT prime, times the product on all negative exponents of xi minus bijt. So in any case, we have defined this matrix that we call B of t. Bijt. It is an n times n integer matrix. So, and maybe we start doing some observations on this matrices. This is defined for all t, okay? For all t in the graph.
It's a square matrix.
Yes, it's a square matrix. Well, of course, if we consider the matrix B of t prime, you can write these monomials also in this form. This is Pj t prime times the product on I such that Bij t prime is positive xi to Bij t prime. I've just rewritten this expression with t prime instead of t. Okay? And now if we look at these two expressions, we have an easy relation between these exponents. This is the first observation that Bij t prime is equal to minus Bij t. Okay, this is true if t and t prime.
Scusa Fabrizio, lì sotto è maggiore di 0 quando tu scrivi meno J, o no?
Sì.
No,
No, è minore perché dopo
non
li
vuoi quelli negativi, gli esponenti?
ma li ha raccolti separati.
Appunto, in MG,
Yes.
in
I want
MG t prime, don't you want the Bij to be negative? The exponents to be negative, sorry.
I want these exponents are negative here, but then if I write the monomial, I want the exponent to be positive.
Ah, that's right. Sorry. That in the quotient they are negative.
Yeah, 1 over MJT prime. Yes.
Sorry.
So this is the first easy relation that we have among these the coefficients of these matrices. Then I want to observe also that these matrices Bt are is sign skew symmetry. So what does this mean? A matrix is sign skew symmetric. Definition: matrix. Square matrix A is sign skew symmetric. If Aij and Aj have opposite sign, meaning that either they are both 0 or they have opposite sign. Either both 0 or have opposite sign. In particular, a skew symmetric matrix, of course, is also sign skew symmetric. So let's verify this this condition for the matrices Bij.
Is it property 3? Property 3?
Yeah, many of these are needed. So we start with
Come? No, deve essere che cioè deve essere meno 2, 1. C'è solo il segno che cambia.
just the sign, yes. So to begin, let's verify that the entries on the diagonal are 0. Biit. So this is by definition the exponent of x to the I in MIT, which is 0 by axiom 1. Then let's see if Bijt and Bjit. So assume that one of the two is positive. If Bijt is positive, this means that this is equivalent to xj divides MIT. And yes, then we apply axiom 2. Axiom 3 maybe. 3. This is equivalent to xi divides m j prime. In our new terminology, this means that p j I of t prime is positive. And then we have to consider this. In this case, we have t and t prime are joined by an edge labeled with I, so I can apply this where the second index is I. So this is equal to minus Bji of t. So we actually have this property of the signs to symmetricity. So all these matrices are signs to symmetric. Of course, this is not enough to be sure that we have an exchange pattern satisfying all these properties. And what we need now is the concept of a mutation of a matrix. So I can give you this definition. Mutation. So we start with an n times n integer matrix B. N times n integer matrix. And we want to define the mutation in direction k, mu k of B. Okay, we call it B prime. The coefficients of B prime are given by the following formula. So B I J prime. So this is minus Bij if one of the two indices is k. So if I equals k or j equals k. Otherwise, we have this expression. We have Bij plus absolute value of Bik times Bkj plus Bik times the absolute value of Bkj.
So you want to know what happens if you move?
Yes.
And then
This is how the matrix changes when we pass from.
And then the cluster will be a sequence of matrices, right?
Yes.
That's the idea. Okay.
So now I will state the exact result in a moment. So this is otherwise. So this is an expression that could be also written in an easiest way, because this is always either 0 or just the product of just product of these two elements.
As a preview, what is the advantage of this matrix thing, with the cluster? Why do we do this?
You do this because you may code all the data in a matrix. And then you know that all the rest is determined by this matrix by a sequence of mutations. So,
and there is an advantage. Okay.
We will see. So this is the result. Family of integer matrices BT Tn comes from an exchange pattern if and only if these two conditions are satisfied. The BT symmetric. Two, whenever we have two vertices T and T prime joined by an edge labeled with K, then B of T prime is the notation direction K of the T. So of course this immediately implies that the mutation is involved. If we apply 2 times the mutation, we come back to the original matrix. And this is a trigger definition. Okay. So maybe I can do this automatically. Okay.
Question. So if we move 2 steps, then we have more than one way to go back, right?
No, because we have a 3.
Right.
So you don't have more than one.
Oh, we have a 3.
Yes. If you move on a 3, there is only one path.
Okay, no, it was a stupid question. So it's never, nothing ever happens. We have a 3, yes.
But maybe I can prove one direction of this proposition. The other one is similar and easier.
Seems to me that the one where you have to verify is simpler than the other one, right?
No, sorry, there is something.
No, the family integral it comes from exchange pattern if and only if these two, no?
Yes.
So there is one way that seems as easy. So to verify that, I mean, if you have, BT prime, when you already have your exchange pattern, then it satisfies. This seems to me an exercise. Is the other way that seems harder, but I don't know.
No, they're actually the same.
They're the same, okay.
Yes. Because all the axioms are
Forcing
encoded
the-
in properties of these matrices and vice versa.
Okay.
So it's not a deep result. I should say that both ways are an exercise, so
No.
I can do only one. But if you want, we can do both.
Do the one that I don't know how to do.
Which one you want to do?
The one that
Constructing the exchange.
suppose 1 and 2 is true, then there is exchange
Okay.
pattern that does it.
Okay.
Okay.
So there is something I don't understand. The fact that k2 squared is the identity depends on the fact that B is scientifically symmetric, right? Or is it true for every matrix B? That remark.
Yes.
Is it true for every matrix B or for any all skew-symmetric matrix B?
I made the verification, but I don't remember if I used that matrix extends to symmetry.
This is just okay.
Let me see. We can do this verification.
Oh, okay, sorry.
I don't know what to write. So at B double prime give the mutation of B prime. We see that B double prime is B. So B double prime ij is minus B prime. So B double prime ij is minus B prime ij if I equals to k or j equals to k, and in this case we have that this is B ij. I equal k or j. So let's see the other case. You can do it here. double prime ij, that is b prime ij plus b prime ik b prime aj plus b prime ik absolute value b prime aj 2. Okay. Then b prime ij is this expression. So we have b ij plus b ik b aj plus b plus. So b prime ik is minus b ik, so the absolute value is the same. This is b ik. B prime kj is minus b kj, minus b kj. And then b prime ik is minus b ik. And this is the absolute value is the same. So I guess that everything cancelled. We just have the Bij. So we didn't use the fact that the Bij, the matrix is explicit.
Thank you.
No problem. Okay, so maybe I can erase this.
Forse non devi cancellare quello che ci serve.
Ah, the definition of notation, yes. But I need a free blackboard to write, so maybe I write the notation somewhere else. Prime then b prime x minus b ij or b Okay, so we want to prove the direction that I wanted to prove. So we assume that B is all the B are sense-to symmetric and that they are linked by a sequence of mutations. And then we look at these properties. So of course, if we start from the matrices, then we define the monomials MIT by product of I such that b I j t is positive xi b I.
Then there is no coefficient, right?
If I want to show that an exchange pattern exists, I can choose the one that I prefer.
So it's not the one-to-one correspondence between these matrices and the pattern?
No, we always have this freedom on the coefficients. But we will study the case of the coefficients in the next lecture. So there will be another matrix which encodes
because the way you presented it, it doesn't contain the same information as the class.
No, we are just dealing with the exponents. In the next lecture, we will deal with coefficients, and they will be encoded in another n times n matrix, having some properties. So all the data will be encoded in n times 2n matrix. Okay. So this is how the monomials are defined. Then we verify the axioms. Axiom 1. Xi does not divide MIT.
There is one J maybe.
Yes, you're right.
MJT.
Sì, è come l'hai definito prima, sì.
Yes, it's MJT. Okay, thanks. Yeah. Oh, xi does not divide m. Using index j. Okay, but xj appears with exponents bjj, which is 0 because the matrix is sensitive simple. So this is this. 2. This 2 pt prime. Maybe I use the letter k here because we used k for the notation. So here we want to prove that xj divides mit and kt. So this is equivalent to b k I'm mixing all these. So now xj appears in mkt with bjk. P is positive. If and only if no, this implies that P J K of P prime is not positive. Okay. So let's see B J K prime by definition is minus B J K. The definition of mutation when one of the two indices is K. So of course if this is positive.
I'm confused. So now B for you, what is B now for you?
P is the matrix that we
the
have
one
satisfying
coming from the mutation. Okay.
We started,
no. Okay, I understand.
We started from a family.
So you're applying the axiom 2 for the matrix to say that.
Yes.
Okay.
Apply that the matrix B prime is obtained from B by the mutation.
Senti, scusami, pazienza.
Sì.
X J divide MK di T, non diventa BKJ positivo di T?
Ma sono
Penso che sia
la stessa cosa,
che sia la stessa cosa, ma
sì, no, certo.
perché si scambia il segno, ma è solo per me
Allora, sono xj MK.
divide MK, vuol dire BKJ di T maggiore di 0. O no?
No,
Mi sembra giusto.
lui l'ha chiamato prodotto.
Cioè, il secondo indice
È quello che
indica il monomio. Quindi quasi sto facendo MK. No, ma è che uso indici diversi a seconda di dove mi muovo, si crea confusione. D'altra parte, se lui mi fa fare quello che non mi ero preparato.
No, rido per Rita, che continua con la sua.
sai, così e così via.
Andiamo al 3. 3 over. You get xj divides mit. This means that b j I t is positive. If and only if x I j t prime, so p I j t prime is positive. Okay. So here the index of mutation is I. Okay. So let me use this property with k equal I. In any case, b I j t prime is minus b I j t. Because I'm doing a mutation with index I.
Because you know that.
So these two coefficients are again in this situation just this.
Okay.
And since the matrix B is sin skew symmetric, this is true. BIJT has the opposite sign to BJI. Okay, now let's see axiom 4, which is of course most difficult. So, of course, in my notes I have a J, K, and J.
It's always like this. When I lecture, I do always the same. I change the indices.
So, let's see how to express this, these quotients, MIT2. So MIT2 divided by MIT1. This is product over J such that B, J, I, T2 are positive. X, J to B, J, I, and below we have the product of J such that B, J, I of P1 is positive of X, J,